Okay, so from Canvas, we can get to this. You can do it straight from your sheet.
Is it the sines and angles, or is it two-dimensional forces?
Two-dimensional forces. It's going to be the one that's listed as like today in class. And there's another one for like due by next class or something like that. So you're just going to look for the one that's the first one, two-dimensional forces. Here we're going to talk about signs hung at angles, and we're going to see.
All students in the cafeteria and gym are released to go to their fourth period class. Thank you.
Okay, hopefully that'll be our last interruption. We're going to look at signs that are hung with different angles, and what we're going to do is take the information that we learned in two-dimensional projectiles or projectiles at angles, bring it into forces, apply it, and just take the foundation that we have in forces and grow it, basically taking two things that we already knew, bring it together as one. So this isn't terrible, but like I said before, there's a bit of a learning curve, so don't be discouraged right at first. You're going to catch on if you stick with me, write the things that I write, and then just kind of stay with us. If you find that you have a question, yeah, go ahead.
There's no link to the worksheet or the notes page.
Here, let's do this. So let's check this out. If I go to,
I'm pretty sure there is a link.
On Thursday and Friday for a week?
Yeah, I just printed it out.
There's no link for me.
On week 8.
For the
I'm on week 8.
forces assignment?
so follow my me online. So I'm going into our class, hopefully. All right, I'm gonna click on coursework. And then forces. And then we're gonna, since today is the 8th, we pick, week 5? Or I'm sorry, week 4. And then in week 4, if I scroll down, this one right here that says signs at angles. So right underneath that indentation. So yeah, it says two-dimensional forces. You have to go to the indentation underneath that. All right, that should take us and get us into the 2D forces, which is this one. Now, I'm going to try to monitor the chat the best I can. Actually, there's something in there right now. So we start in 2 minutes. Yeah, we're almost 2 minutes from the time you asked me if you can do that. So try to make your questions audible, because it's going to get my attention faster. Also, if I make a mistake, which is completely likely that I can make mistakes, I want you to catch those mistakes sooner than not, and so everybody can kind of be on the same pace. I will look at the chat from time to time, but I may not be as quick on it. So just get audible. It's okay. Yell at me, laugh at me, point at me. That's totally okay. But let me know where the mistakes are. Fix it for the group. All right, let's get started. So if this is a sign in the center and it tells us this is 10 kilograms, so this is 10 kilograms in the center, let's call this a wall right here. So there's a wall, and let's say it's a storefront, and maybe this is even a roof. So all this, this is a solid roof, solid wall. And the reason I kind of highlight that is this sign's not moving. It's attached to a solid wall. It's attached to a solid roof. This sign is not accelerating in the vertical. It's not falling down and speeding up. It's not speeding up to the ceiling, the sky, the clouds, the birds. It's not moving horizontally with any speed. It has a constant velocity of 0. Constant velocity means no acceleration. But bigger than that, it means balanced forces for us, meaning whatever's pulling it to the left is balanced to what's pulling it to the right. Whatever's pulling it down is also pulling up. So all of that is known. Let's start diagramming this and see what we have. Now, one bit of information that should have been on this worksheet that's not, it's an error in the worksheet. It's not something you have to come up with your own. You don't have to get a protractor out or anything, but we need to know the angle. So the angle I'm going to put in is 30 degrees right here. Again, it's not something you would have had to derive for this particular problem. They should have told us that in order for us to solve what the tension in each string is. Okay, I also want to identify the strings because I want to be able to talk intelligently with you which one is which. So let's call the one on the top T1. Let's call the one to the left T2. It'll just make it easier as we diagram these to be able to say, hey, I'm talking about T1, I'm talking about T2. Now T2 is pulling that sign to the left. T2 is pulling the sign to the left, where T1 is pulling the sign upward and also to the right. We can see that based on the angle that it's coming off of the sign, the 10 kilogram sign or object, whatever you want to say, doesn't matter. So if T1 is pulling it two different directions, we want to break that into its components. We saw that on the test, I believe, or at least on the review where it said, draw the free body diagram, but don't use components. What it's saying is if a force goes off at an angle, draw it at an angle. When you write or create the free body diagrams for a test, you're just going to have your dot. You can draw a box around the dot if you like, but you're going to draw the arrows according to the magnitudes of the forces and in the direction that the force is pulling. In this case, since we're working the problem, this is kind of our scratch work. So we can make a mess if we want to, and we're going to come up with a component so we can say, how much is it pulling upward? How much is it pulling outward? So if I change my colors here just for contrast, I can say that T1 is pulling up, and it's also pulling to the right. So overall, you have this hypotenuse to the triangle, but you have a component of it going up and a component of it going to the right. If I was to look at those components, since my angle is here in the corner, the opposite side of that corner, I would use the sine function, and the adjacent, I would use the cosine function. So for the upward component of T1, we can call this T1 in the y direction if we really want to. And this would be calculated by saying that's equal to T1, it's the opposite side, so that's sine of the angle 30 degrees. For the part that pulls it to the right, that's T1 in the x direction. So if we want to, we can call this T1x. I don't care what you call it, I'm just giving it a name so I can differentiate. And I would calculate that by saying, well, that's adjacent to my angle. So I'm going to call that hypotenuse T1 times the cosine of the angle 30 degrees. So now I've taken T1, the tension of 1, and I've broken into part of it pulls up, part of it pulls to the right. That's all we've done today, and that is your complete lesson. Sort of. That's the idea behind the lesson. Now let's use all the things we already know and do some cool stuff with it, okay? Now in the horizontal, meaning the left and the right, we said our forces are balanced because there's no acceleration, balanced forces. Balanced forces, what does that look like? How would I show balanced forces? Someone talk to me. Tell me what balanced forces means or looks like. Come on, talk.
Net
All right, I want more people talking. Come on, talk over each other.
force 0.
Zero net force.
All right, zero net force. How would I show that in an equation? Could I say something is equal to something?
Net force equals 0.
Okay. So what if net force, that means I would take my force to the left, subtract my force to the right, and say that's equal to 0. What if I were to add that force to the right to the other side? Couldn't I say that my force to the left, T2, is equal to the force to the right? In this case, it would be T1 cosine of 30. Couldn't I say that? My left side is equal to my right side because they're balanced. And if I could say that in the horizontal, what could I say in the vertical? What would be equal to what?
Gravity would be equal to T1 sine 30.
Exactly right. Now gravity, that's the force down, Fg. And Fg is calculated by mg. So I'm going to use mg sometimes Fg. They're interchangeable. Today I feel like an mg kind of day. So I'm going to say mg down is equal to all the forces up. And my only force up, just like you said, is T1 sine of 30. Now from this, just a simple yes or no, could we solve for all the variables?
Yes.
Yes or no?
Yes, but you have to do it in steps.
Absolutely got to do it in steps. Which one do you want to solve for first? If I number these equations 1 and 2, which one should we attack first?
2.
2.
Yeah, absolutely 2. I'm going to work downwards from number 2.
2, yeah.
So the mass, so we have mg, which is mass times the acceleration of gravity. That would be what, 10 times 10 is equal to T1 And now sine of 30. Don't forget your calculator has to be in degree mode. So if you're using a scientific calculator, click the mode button every time you turn it on when you're going to use sine or cosine. Just confirm. You don't want to do all this work, get everything wrong because you're in the wrong mode. Show that you know what you're doing. Check, you're in degree mode, perfect. I'm going to type into my calculator just simply sine 30, enter, and I got 0.5. So 10 times 10 is equal to T1 times 0.05. 10 times 10 is 100. So I'd have 100 is equal to T1 times 0.05. Ooh, I'm sorry, 0.5. And if I divide both sides by, hang on a second, let me fix this because the way I've written this looks terrible. 0.5. If I divide both sides by 0.5, cancels on the right, you guys know that part. And 100 times divided by 0.5 should give me 200. 200 newtons is equal to T1. Not too bad. We can handle this stuff. Now, if I go back up to equation, the one that I marked as equation 1, and just like give myself a big arrow to say, hey, I'm moving this over here, I've got T2 is equal to T1, which we said was 200, times the cosine of 30. So let me get the cosine of 30 from my calculator. It tells me it is 0.87 times 0.87. So T2 is equal to 200 times 0.87. In my calculator, I get 174 newtons. There, we've solved for both of those tensions simply by using something that we learned in kinematics with projectiles at angles. We're breaking those angles into their components, vertical and horizontal. If the object is not accelerating, it could be moving. As long as it's not accelerating, the leftward force is equal to the rightward forces. The upward forces are equal to the downward forces. They're balanced. All right, now, that's the complete lesson, at least 2/3 of it. We're going to do a little bit more with sines. Then we're going to look at an object at an incline. And then when we're done, we'll take a look at the homework. All right, so what popped into the chat, I happen to have it open. I said I wouldn't, but I did. So if we know the exact value of these sine and cosine values, like cosine 30 is, can we apply that and make them a decimal in the end? Yeah, you can leave it as a fraction. That's completely fine. And then convert to a decimal in the end, that's completely fine. And I understand there's going to be rounding along the way. In the short term, rounding along the way, we always account for that. In the long term, like for your test in May, you're not going to use variables. You're going to leave it as T1 cosine 30, or actually it'll be T1 cosine theta. So you're not going to have hardly any numbers at all. So make sure you're getting used to the variables as much as possible, All right, I'm going to scroll this up. Let's look at number 2. I want to take this slow. And I know many of you are like, I got this, let's move on. But if we just take a breath, take it slow, make sure everybody's secure on this, it will make the quiz we take week after next really easy. So let's take a look. Let's scroll this up. Okay. Now we've got a block of mass 8 kilograms. So I'm going to go ahead and write 8 kilograms into the block. So 8 kilograms. It's being pulled by a string with a force of 50 newtons. So we have a tension because it says string. So string means tension. 50 newtons, that makes it 20 degree above the horizontal. There's an angle there. Okay, so that means I'm pulling this like that. My tension is equal to 50 newtons. And it said 20 degrees to the horizontal. So if I make the horizontal like this, that's the horizontal. My angle would go right in here, 20 degrees. So I've got 20 degrees to the horizontal at tension of 50 newtons. Okay, it tells me the coefficient of friction between the block and the surface is 0.2. Okay, I'm gonna go ahead and box that in so I don't lose it. It wants me to draw a free body diagram for the block. So this block where I've put the 8 kilograms, I'm gonna use, this is gonna be my scratch work. Okay, I'm gonna do all my scratch work in it. I'll do the free body diagram under the area where it says draw a free body diagram. Because a free body diagram should not have numbers. It should just have arrows that have the length, their length is indicated or dictated by their magnitude of the force, and they should point in the direction of the force, no components. On question 1, how'd you know it was 30 degrees? That's a good question. On question 1, the worksheet was supposed to tell us, but there was an error in the worksheet. You won't have to derive it. You wouldn't have been able to derive it without me telling you, without more information. So for number 1, I knew the 30 degrees only because the worksheet mistakenly was created without it. So the teachers decided 2 years ago, hey, let's make it 30 degrees, and we went with it ever since. So that's not something that it should have told us, Okay, so looking at this one, I know that when I pull something, it's not hovering, it's usually on a counters or a floor or something, it's on a surface. So I can say, hey, this is gonna have a force normal. It's gonna have a force of gravity because I'm still on Earth so far. And they gave me a coefficient of friction, so it must have a force of friction. Force of friction, okay? Now, given all that, I've just taught us and talked to us about how we want to break tension into its components. So we've got this horizontal component. Let's go ahead and draw the vertical component. It goes up like that. I use those dotted lines just to show that it's a component. It's not a requirement, just the way I do it. So for the tension in the horizontal, I would say that tension in the x direction is equal to 50 cosine 20. And I would say that tension in the y direction is equal to 50, the hypotenuse, times the sine of the angle, 20. 50 sine 20. So I've got all of my forces laid out for the most part. I can solve some things, but let's go over to the free body diagram. Let's draw that the way that we would if we're turning it into a, for the second question degree, is it 20 degrees? Yes, it tells us that like right there. So it's 20 degrees. I'm sorry, my script too, sometimes it's pretty, sometimes it's not, but yeah, 20 degrees. And I might be able to zoom this in just a touch so you can see it better. Let's see, that might help a little bit. If I'm drawing a free body diagram for an actual test, let me change my colors of my pen. And let's say, okay, I'm gonna totally go professional and make it black. And we'll say, okay, a free body diagram on a test. They give us a dot. Maybe we want to draw a box around it, maybe not. But I would say, okay, in this, my force of gravity down, so I'd have Fg. I've got another force of tension that's 50, so it's going to go off like this. It should be a little bit smaller than the force of gravity because it's 50 compared to 80. So this would be my tension. My force of friction, let's say, might be something like this. And then my force normal. In this case, it's not going to be the same as force of gravity because it has tension helping it out. So I might draw it something, maybe something like this. Now I have the ability, once I calculate all these, to go back to this and erase it and adjust the arrows, because when you turn something in, you want it to represent exactly what you know. And you know that a free body diagram for a test looks like this. This is test. This is my scratch work. Okay, the scratch work is what's going to help me answer questions. The test answer is showing the test appraiser, I know what I'm talking about and I deserve that 100% on this test because I'm smart. And I've proved it to you because I've done all the stuff, right? All right, so let's scroll this up just a touch and then let's start answering some of these questions. Let's choose purple because purple's fun. How much of the 50 Newton force is in the horizontal direction? Now, don't tell me the number, but tell me, where am I going to find this information? Identify that in my scratch work. 50 Newton force in the horizontal direction. What did I name that? I gave it a name.
T of x.
Yeah. All right, so that's Tx. And what's Tx equal to? How do I calculate it?
50
50 cosine 20.
Perfect. So we're just looking at the diagram. If anybody's not keeping up, they're looking at this and they're like, it's right there. That's the horizontal component of that 50 Newton tension. So I'm going to go to my calculator. I'm going to type in the scientific calculator, you simply hit 50, cosine 20, enter. Here I got 46.98. 46.98 newtons. If you have, yeah, go ahead.
Is it okay if we round it up to like 47?
If it's only by 0.02, yeah, absolutely. If it's by 0.02. Now, if it's like, 46.4 47 and you want to make it 40, I would tend to go keep the 2 decimal places, but since we're only talking about 200ths, that's not going to hurt you. That's totally going to be fine if you're only talking about 200ths of a place. Totally.
So is there like a specific range in which your answer has to fall on the AP exam if you round up? Like, is
on
there
the
like a
AP
range?
exam, they're not going to give you variables. On the AP exam, your answer is that right there.
Okay.
Only on your AP exam, it would be like, you would say, let's see, you would probably put, it would be Tx is equal to tension cosine theta. That would be your answer on the AP exam. Because the 50 is the hypotenuse, which is just tension, and you'd say the cosine of the angle. So that would be your answer. Let me box it in because right now it looks like a dividing problem.
So in our, so on the AP exam, your answer is going to be based on the variables. There's not going to be like any like numerical components within it.
Very few numbers. They want you to be able to do that test without a calculator.
Okay.
Because, with a calculator, you guys are smart and you know how to program these calculators to do a lot of things for you. And the AP exam really wants to know what do you know and not what you can get someone to program into your calculator. So someone asked me, is the AP exam in school or online? As of a week or 2 ago, Frisco Independent School District said if the school doors are open for business, Frisco ISD students will take the test at their home campus. So if you're, now that's assuming something with COVID virus doesn't get worse and our doors close. If our doors close, different issue. But the plan for Frisco ISD right now is you'll take the test on campus traditional. Now, again, that's in May. There's a lot of weeks between now and May, and I don't make those decisions. So I'll tell you as I know things, but there's no purpose in arguing with me because I don't make those decisions. They don't even ask me my opinion. I'm here to help you guys get to the 5, whether you do it at home or you do it in the gym. Either way, I want you to make a 5. Let's see. Oh, I was going to tell you, in the calculator, we're hitting 50 cosine 20. If your calculator runs out of batteries and you have to grab your cell phone to calculate these, you're going to turn your phone to the side. I'm going to do it for an iPhone. So you turn the phone to the side so you get the scientific calculator. You would type in 20, hit the cosine button so it does the cosine of 20 for you. Don't hit equals, it does it for you. 20, cosine button, then times 50. So you have to do it backwards in a cell phone. But that's just saying like your calculator ran out of batteries because most of you, if not all, probably have a calculator at the ready. And let's look at C. We've done B. How much of the force is in the horizontal direction? What about in the vertical? What's the name of the vertical direction of this?
Ty?
Ty.
Ty. And then how do I calculate Ty?
50 sine 20.
And when I put that in my calculator, 50 sine 20, I get 17.10. So what we're seeing is, let's see, we got 46. We had a total of 50 newtons of tension. We had about 47 horizontal, and we've got about 17 vertical. So they're not going to add up to be 50. Of course, this is a right triangle. A squared plus B squared should equal C squared. So Tx squared plus Ty squared should equal the square of the tension. I'm not going to go and check it right now because proving Pythagoras is not on my agenda for today. If you're so inclined, go for it, but let's not have that discussion in class. But what's more important is the normal force. What is the normal force on this object? Now, before I scroll back to the picture, is the normal force balanced with the force of gravity for this object? Yes or no? Talk to me.
Yes.
I want to hear votes from a lot more people. Yes or no? Just say it. I'm not looking at the screen. I'm not judging you. Tell me yes or no.
Yes.
No.
Yes.
No.
Yes.
No.
No.
All right. I think I heard 2/3 yes, 1/3 no, and that's a very unscientific poll. But let's take a look at things. Before I scroll up, let's make some agreements real quick, okay? Is this sign accelerating? Yes or no? Is the sign accelerating?
Yes.
Yes.
The sign is in motion, it's accelerating?
Yes.
Oh, I'm not sorry, that's not a sign, this is an object. So the sign is in the vertical, is it accelerating?
No.
Probably. I think so.
All right, probably. I love the non-committal, but still giving an answer. It's like, I'm not going to say for sure, but probably. I love that. That's my favorite answer of the day. So that made my afternoon. I appreciate that. Let's go back up to our picture. We're dragging this object horizontally. So we may be accelerating horizontally, but as far as the vertical, the up and down, we're not accelerating. Okay, it's dragging along the ground. Imagine a kid has got their toy with a string tied along around their, the toy, and they're just dragging it as they're moving along, through the house or whatever. So in the vertical, it's staying on the ground, so it's not accelerating. So we're going to have balanced forces
Wait, how do we know that?
because we're pulling it sideways. We're not pulling it up, right? And if we're pulling it up, we can only pull it up so far. Our arm is so big. But imagine if you've ever seen a little kid pull a wagon, you know how the wagon arm is at an angle, and then as they're pulling it, the wagon is moving side to side, but it's not moving upwards. That's what we're seeing here. That's what this situation is. It's being pulled by a string with a force of 50 newtons. We've got a coefficient of friction, degrees above the heart. Yeah, all this would indicate it's dragging along the ground at that angle. Well, at least the tension of the string is at that angle.
So will we talk about slopes later?
Yeah, the very next question. Or the next, number 3 is going to have a slope. So yeah, number 3 is going to be a slope. So we're, for this one though, tell me, now that you're looking at the picture, if we know there's no acceleration vertically, is force normal equal to force gravity?
No.
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 Right, because if we look at that picture, we should be able to say that the force of gravity is equal to, the force down is equal to the force up. And the force up was force normal plus tension in the y direction. If we rearrange that, we would say that force of gravity minus the tension in the y direction is equal to the force normal. That shows it's smaller than the force of gravity. If we were to plug in some numbers, I think I still have some room. Let's see what those numbers were. All right, 8 kilogram object, so the force of gravity is going to be 80 minus Ty, which we said Ty is 17.10, is equal to the force normal. And then let's see, that'd be what, 62.9, I think, 62.9 newtons equals force normal. If I did that in my head, so if I get it wrong, you got to tell me. But 62.9, I believe, is the force normal, which is less than the force of gravity. So how did I get this? We've determined through our discussion and looking at the problem that vertically, up and down, there's no acceleration. This object's being dragged along the ground and is not moving vertically. It's not moving up or down. It's simply moving along the ground horizontally. So if there's no acceleration in the vertical, all downward forces equal all upward forces. So we're going to add up all the downward forces and set that equal to all the upward forces. There's only one downward force. Let me scroll so you can see it. There's only one downward force, force of gravity. And that is equal to all the upward forces, which would be force normal and tension in the y direction. So tension in the y direction plus force normal together give us all the upward forces. And then force gravity happens to be a lonely force today, all by himself, but he balances force normal and tension in the y direction. Okay, so that is how we put together question D. So force normal and force gravity cannot be the same because of tension in the y direction. Correct, absolutely. We've added a force in the upward. It would be the same as if I had an object and I pushed downward on it, like my calculator on the countertop. Before I touch that calculator, it just has force gravity down and force normal up. They're balanced. But if I push down on this calculator, so let me move my little screen here. If I push down on my calculator, I'm applying a downward force. That calculator is not moving, right? No acceleration. So it must have balanced forces. So in this case, my downward force applied plus the force of gravity downward must be equal to the force normal upward. So here the force normal went up because I increased the downward force. When we created a force upwards, The force normal balanced it by decreasing. That force normal seems to be kind of an intelligent force. It keeps things balanced sometimes, and it responds to the environment. In these cases, we're showing that. If I push down on something, force normal went up. If I pull up on something, force normal went down, assuming balanced forces, assuming balanced forces. Okay. All right, so that gets us through D. I bet you can probably guess, if I just got force normal, what do you think I'm going to calculate next? Just a big guess.
Friction.
Yeah, friction. We remember friction is fun. I mean, not really fun, but hey, friction, force of friction is equal to the coefficient times the force normal. We said the coefficient, if I remember correctly, was 0.2 times the force normal that we just calculated, 62.9 newtons. You guys have to keep me straight. If I get anything wrong, I'm going to blame somebody besides me. Just kidding. It's totally my fault. 62.9 times 0.2 gives me 12.58. 12.58 newtons is my force of friction. Let me box this in. Okay. I think we've solved for all the forces. Tension in the X, tension in the Y, force normal, force gravity, and force of friction. I think we've got them all. The very last question for number 2, the last one they're going to ask us is, what is the acceleration of the block? All right, this is our opportunity to say, I remember, let's see, do we ever specify the direction of force of friction? We did in our free body diagram. So someone asked, did we ever specify the direction? Well, we know that the force of friction resists motion. So if we're pulling it to the right, force of friction must be to the left. All right, so let's go back to this. And then what is the acceleration of the block? Here, we're going to show our amazing knowledge of Newton's second law with a very complicated formula, being sum of forces is equal to mass times acceleration. Yes, that is it. We impress even ourselves. So I'm going to divide both sides by mass because I want to solve for acceleration. So that cancels the masses there, and I'm just going to simply say sum of forces divided by mass equals acceleration. All right, so now we need to look at the sum of forces. We've said it's not accelerating vertically, so we're only looking at the sum of forces horizontally. So here we had the force to the right, that would have been tension in the X direction minus the force of friction. Let's look at the picture and see if I'm right. Let's come back up here. Yeah, all right, so we have tension in the X direction that's going to the right, and we have force of friction that's going to the left. So we've got all that. All right, and that's going to be equal to, I'm sorry, divided by the mass. And the mass was 8, wasn't it? A terrible memory, 8. So let me scroll back. Sorry for all that scrolling, but it helps me see that. So we'd have divided by the mass equals acceleration. Tension in the X, let's see, this is going to be 8 on the bottom. Tension in the X, we said was 46.98. Okay. We've already solved for this. 46.98 minus the force of friction, which we said was 12.58. Divided by 8 equals acceleration. Let's move this like up here. So 46.98 minus 12.58, enter, divided by 8 equals 4.3 meters per second square equals the acceleration to the right, because that's what the direction of my net force. And I can box that guy in right there. All right, take a look at this. I want everybody to catch up. Ask any questions that you have about number 1 or number 2. Either one is fine. I'm gonna give you another second. I'm gonna take a drink of water. Everybody take a breath, stretch. Then we're gonna do that one question with a box on an incline. And then we're going to work on the homework just a little bit together. Then I'll turn it over to you guys. While we're thinking and letting our brains just relax for a second, let's just talk about the direction of what the next few days are going to look like. Today's A day, Friday's B day. We're going to get the homework done in class today, so we get to go into a 3-day weekend with no homework, meaning Monday is a holiday. Tuesday is going to be an A day. On Tuesday, I hope to have everybody's tests graded and FRQs graded before then. On Tuesday, you'll be able to see all my, by Tuesday, you'll see all of my notations for your test. You'll be able to do test corrections, kind of look at what you missed, be able to do any kind of work and answer those questions, basically test corrections, remediation, that sort of thing. That will be Tuesday. Wednesday is PSAT. So if you're a sophomore or junior, you're going to be testing PSAT. If you're a freshman or a senior on your B-Day classes, they will give you something to do online so that you can show that you were engaged in doing schoolwork that day. That brings us to Thursday, Friday of next week. We meet on Thursday. It's A-Day. We're going to continue with objects on inclines. So we're learning today, Thursday. We're going to learn again next Thursday. Objects on inclines. Also Thursday, Friday, retests will be open. It'll be a gated timed retest, I think 30 minutes, and we'll give you a big wide open time to get it done sometime between Thursday and Friday. That brings us to the next week. So not next week, but the week after, 2 weeks from now. Monday, Tuesday, we'll do review. Wednesday, Thursday, we'll do quiz on 2D forces. So we're learning today. We're going to learn on Thursday of next week. Then we do review and quiz. The quiz will have 2 parts, an FRQ and a multiple choice section. It'll be 2 separate minor grades, and there will be no test. We're going to go directly into the next topic, okay? So the quiz won't have a test replacement, so we want to make sure we perform well on the test. Let's see, what is the next topic?
Glitched out for me. Can you say when the quiz is again?
The quiz is going to be, let me get a calendar out, and I'll do a better job of telling you the exact date. All right, so today's the 8th, 9th. The quiz will be on the 19th. Monday, I'm sorry, that's the review. The review is Monday the 19th. The quiz is Wednesday the 21st, since we're in A-Day. Quiz is 21st, Wednesday the 21st, 2 weeks from yesterday for A-Day.
And that's a minor grade, right?
It'll be 2 minor grades, 1 multiple choice section that's a minor grade, and 1 FRQ section that is a minor grade. So 2 minor grades, plus the review on that Monday will also be a minor grade. So that week, on Monday, you're going to get a minor grade, and that Wednesday, you're going to get 2 minor grades. So you're going to have 3 minor grades all in back-to-back days. And yes, all of this will be on the next 9 weeks. We still have retests for this 9 weeks, but I don't think we have any other new grades for the current grading period. No new grades. I still have to get your test grades in, yes. You still have an opportunity to retest up to an 85, yes. But there's no new assignments, tests, or quizzes that we're going to do between that now and the end of next week that would apply to this 9 weeks. Okay, let's take now that we've had a chance, let me actually take that drink of water. Okay, let's take a look at this next section. It's not going to be terribly different. Little bit different, but not terribly different. So stick with me on this. I'm going to show you a couple of tricks, a couple of things on how to solve these problems. It'll make them easier, and then we're just going to go for it, okay? So we've got an 8-kilogram block is at rest on an inclined plane and is held in place by a string. Okay, so since this is a string, this is tension, and it's at rest, so I'm going to block that in, okay? And so what I've got is I want to draw gravity. Now, gravity always, always, always goes straight down. Force of gravity. But force normal normally is in the same plane as force of gravity, just going the opposite direction. But in this case, our surface is at a 30-degree angle, and force normal is perpendicular to the surface. So that means force normal is going to go this way. It goes straight up from the box at whatever angle the box is on. Do we see that? How the force normal is kind of tilted to one side, tilted to the left a bit? And then we could say, well, we might have force of friction this way. Probably do since it's at rest. Maybe. We'll see. So now I've kind of drawn those. Now, if I have to draw, oh, go ahead.
Do we assume that since the tension is moving in the leftward direction, since the tension is on the right side, we assume that friction is always on the left?
Yes, because tension is pulling upwards right here, correct?
Yeah.
So tension is like, as if the tension is pulling it up, friction is going to resist that, so friction is going down. Now, if the tension were to loosen and allow this box to slide, then friction would be up. So for right now, I'm going to say friction is down because the tension is pulling up on it. But if tension were to loosen, then friction could be drawn on the right side.
Okay.
That's total valid. And we'll see things, I hope we'll get to them, where we'll see things where friction will actually change directions because an object changes directions. I hope to see a problem like that. It won't be today, but it's kind of cool because it's like, all right, this object slows to a stop and then starts to reverse direction. And you got to say, oh, well, at that moment, friction went from this way to that way. Okay, makes it kind of fun, like a puzzle, right? If I'm drawing this free body diagram for a test, I'm going to show exactly what that would look like I did before. So I'm going to have a dot right here. I can draw a box around the dot. That's cool. Force of gravity always goes straight down. In this case, force normal would be like off to the left a bit. Tension would be up to the right a bit. And force of friction would be that way. So force of friction and tension are linear in this, in what I've drawn, but they're tilted counterclockwise from horizontal. And then force normal should be 90 degrees from, oh, that's not, why did I put force normal twice? Hang on a second. That should be force of friction. Force of friction. There we go. So force of friction and tension should be linear to each other according to the original drawing. Force normal should be 90 degrees to them because it's 90 degrees to the surface. This is how I would answer a question, a test question. Test. But we need to do our scratch work to solve our problems. So over here, I'm gonna do my scratch work. I'm gonna change my color of my pen because purple's more fun. Now, my brain goes crazy trying to understand horizontal and vertical forces if those forces are not horizontal. So what I want to do is I want to take my computer screen and I want to turn it, right? Like if I take my computer right now and I turn it, so that way that box looks level to me. So if you can see my screen, you can see that I'm turning it, the camera, so that I can see that that box is straight. Now, when I see that that box is straight, I want to draw it that way. It helps me do this, okay? So if I drew this box straight, it would look like this, and I'd put 8 kilograms in it. Now I can draw the force normal straight up, force normal. I can draw tension to the right. I can draw friction to the left. But force of gravity, since I've tilted my box, my force of gravity now goes over here. Okay? Bear with me for just a minute, okay? Hold the questions and the anxiety just for a minute, okay? I get it, it's real, it's totally real, but bear with me for just a second, okay? What if I said there's a component of the force of gravity that does go straight down and a component of the gravity that goes off to the left? Since this is a 30-degree angle, that means that force of gravity is offset by 30 degrees. So I would put the 30 degrees right here. No, I don't have geometry all laid out for you to show how it goes back and forth, but what I'm telling you is for however much of an angle I put that box on, that's how much the force of gravity moves from normal straight down, okay? So what I would say then is my force of my FG in the downward position, this would be, going down would be what? FG times the cosine of 30. And then my component of gravity that's going to the left would be FG times the sine of 30. By doing it like this, for me, now I can see leftward forces, I can see rightward forces, I can see up forces, I can see down forces. Does every teacher teach it like this? No. No. But to me,
Mr. Watley?
Yeah, what's up?
Why is the 30 degree, why is the 30 degrees in between the vertical component and the hypotenuse and not the horizontal component, not the hypotenuse?
Okay, let me ask you this. If I were to take that original wedge that says 30 degrees and I were to flatten it out and say 0 degrees, gravity would be going straight down, correct?
Yes.
Think of that force of gravity right, let's see, right, I'm looking at this one right here. You see where I'm drawing the arrow?
Mm-hmm.
All right, I'm looking at this. Now, where the force of gravity is pitched to the left, if I were to have said, hey, that 8 kilograms was sitting flat on the ground, wouldn't that force of gravity point straight down? Normally, if that 8 kilogram box is on level ground, doesn't force of gravity go straight down? You got to say yes. Totally have to say yes.
I'm sorry, I'm on mute. I did say yes.
All right. Now, if I were to then put this box up against a wall, wouldn't force of gravity then be turned a complete 90 degrees, pointing to the
Yes.
side of the box? Okay. Now, so we said that if the box is on level ground, it's pointing straight down. If the box is then against a wall, that force of gravity shifts and is pointing to the other side of that box, right? Now, for every degree that angle increases, that force of gravity shifts away from straight down relative to the box by that 1 degree. So if I increase this will shift out, this will get bigger, right?
Okay. Yeah.
And so there's no way for me to say, okay, these are two parallel lines, so I'm just going to translate this up. What I'm going to say is for me to work this problem, the bigger the angle, the further that force of gravity is going to point to the left instead of straight down in this figure, saying that the force of gravity is going to make this box slide down the hill instead of push down into the hill. And that's why we're going to put it that way. We're going to put it there. So whatever the angle is, we're going to use that angle and say that's how far over the force of gravity has swung. As far as this guy right here, how far over that swings is based on the angle over here in the picture. Outside of that, I'd say just go with me on it. But if we can imagine, okay, the bigger the angle, the further over that thing's going to swing out. So, okay, bigger the angle, that's where that angle is going to go. Okay, so now let's go back to this and let's, it says draw a free body diagram of the mass. Okay, that's what this is right here. We've drawn the free body diagram. I'm going to see if I can clean up some of this. Oh, that was awesome. It actually took away exactly what I wanted it to. Let's get rid of that. Let's get rid of that. Perfect. Okay, draw a free body diagram of the mass. We did that in black over on the left side. That's what we would turn in on a test. We could calculate any of these values, but let's see what it asks us to do. It says, is the normal force acting on the mass greater than, less than, or equal to the weight? Okay, what is the weight? Is there another way for me to define the weight? What force is that?
Gravity.
Gravity. Yeah, so Fg. So let's make a comparison of Fg and force normal, okay? What could we say regarding, is force normal bigger, less than, or equal to force gravity?
Less than,
Bigger.
Okay, why?
because F force normal is equal to the vertical component, horizontal component of force gravity.
You were right with the vertical. You were right with the
Or
vertical.
it is vertical. It is vertical.
Yeah, so since this box is not moving up and down, it's not moving left or right, our vertical components are balanced. So our Fn is equal to that's the upward force, that's equal to the entire downward force. In this case, the entire downward force is force of gravity times the cosine of 30. Okay, the force normal is equal to just one component of gravity, not all of gravity. So that means force of normal is less than Fg because it's equal to just a fraction of Fg. Part of Fg is pulling down the hill, part of Fg is pushing down into the hill. So in this case, force normal acting on the mass is less than the weight of the block because it's equal to just one component of the weight, not the entire weight. That was really good, very good. I think there's only one more question on this whole worksheet. Let me just scroll and make sure. Yeah, that's true, that's true. All right, what will happen to the tension in the string as the angle is increased? Let's go back to the picture. If I increase that angle from 30 degrees to 45, and then from 45 to 90 degrees, and the block doesn't move, it stays at rest. Tell me what happens to the tension in the string.
It increases.
Why does it increase?
Because it has to
Because-
hold the block from going down.
The vertical component of gravity becomes larger.
The vertical component of gravity is going to be bigger. If we go all the way to a 90-degree incline, all of gravity is pulling against the tension instead of just one component. If we go to a 0-degree incline, none of gravity is pulling against the tension. So as we increase the angle, the component of gravity that is opposing tension increases. And if this block is to stay at rest, we need balanced forces. Now we can try to do things to answer these questions as best as we can. We can use physics facts. We can say for an object at rest, there is no acceleration, meaning the forces are balanced. In order to maintain balanced forces, as we increase the angle, the component of gravity increases in the leftward direction. Therefore, tension must make up the difference and increase in the rightward direction. Anything like that. We're trying to say, hey, here's a fact about physics, and this is how it applies to this question. Someone asked me, can I explain again B, number 3B? The normal force, let me scroll to where you can see this part right here. Okay, what I just boxed in. What I'm showing here is that in the picture that we drew, the upward force is equal to the downward force. Because it said the box was at rest, upward force equals downward force. Well, the upward force is just the force normal, and the only thing we have pointing down is force of gravity times the cosine of 30. Force of gravity times the cosine of 30 means that is a fraction of the force of gravity, not all of it. So if force normal is equal to just a part of force gravity, that means it's less than force gravity, because we were able to break force gravity up into two different components, and force normal was equal to one of those components. So that means it's less than the whole thing, because it's only equal to a part. Can you explain now how normal force to be equal to gravity again on the inclined plane? Okay, I think that's what I just hit on. Sometimes for these two, it takes a little bit of experience. Let's look at these questions. Let's practice them. For the inclined plane, the one we just did, we're going to do more of that 1 week from today. More of that then. For today, there's the due by next class in Canvas. I'm going to bring that up, and I'm going to give you some prompts for the first 2 questions, and then I'm going to let you take it from there. But I want to give you a starting point. Can you explain part C again? Let's go to parts. What will happen if the tension, if the string, as the angle is increased? As I increase the angle, the component of gravity moving to the left would be increased, according to my free body diagram. So as I increase the angle, the force of gravity opposing the string would increase, or the component of gravity opposing the string would increase. Since the object is going to have to stay at a standstill at rest, imagining or supposing the object stays at rest, tension then has to increase to balance that increase of the component of gravity pulling to the left. So increase the angle, the component of gravity pulling you down the slope increases. So tension then would have to also increase to oppose it to keep things balanced. Okay. Now take yourself a second and get yourself something to drink, stretch. I'm going to switch over and bring up the homework problems. Let's take just a second, digest that, and then I'm going to give you some prompts to how to get started on this. Not too much different than what we've been doing, but I want to make sure you have a good starting point. Okay, now as I'm working these problems, I'm not creating the formal free body diagram like we're submitting it for a test. I'm not going to do the dot and draw the arrows. I want to do scratch work because I want to show you the thought process. I want to teach you the thought process, and I want to assume you could draw a free body diagram of just drawing the arrows and not doing the components of the forces. If you have problems with the free body diagrams, communicate with me. But I want to teach you the thought process so that you can solve these problems without an issue. Let's see, let me leave through, will you, the recording cover? Yes, I'm going to use this class for the recording today. So it'll be a couple hours after class or maybe sooner. I'm going to post 4th period today in Canvas for the Zoom. So it'll be your class that gets posted. So yeah, if you have to leave, I completely understand, but all that information will be here and you'll see your particular class. So let's take a look at this problem. I've got T1 and T2. And let's see how much of this I want to occupy. If I do use the geometry, I know that whole angles and which angles do I use are difficult. If I were to draw over here and say T1 has a component pulling to the left and has a component pulling up, I could say that this purple line and this line up here at the top, those are parallel. So if this is 60 degrees, that means that this is 60 degrees. Same thing over here. T2 is pulling to the right and up. So I'm marking the right and I'll mark the up. If this is 35 degrees, this is also 35 degrees. Now this is on Earth, presumably. So I could say that pulling down, I've got mg, force of gravity, calculated mg. If I wanted to break T1 and T2 into its components, I would say the horizontal component of T1 would be what? T1 cosine of 60. The vertical component would be T1 sine of 60. Remember, the opposite of the angle is sine, the adjacent to the angle is cosine. I'm going to do the same thing for T2. For the horizontal component, this would be T2 cosine 35. And then the vertical component would be T2 sine 35. Now, if I wanted to use my summation of forces boxes, I could say that in the x direction, the horizontal, that T1 cosine of 60 is equal to the T2 cosine of 35. My only force to the left is equal to my only force to the right. They're balanced. In the y direction, the vertical, the up and down, the only force going down is mg. So mg is equal to all the forces pulling up, which I have T1 sine of 60 plus, I'm writing Ti, that's a T1, I'm sorry, T1. T1 sine of 60 plus T2 sine of 35. I get so used to TI like Texas Instruments, I just write TI instead of T1. So I've got my forces, right? My summation of forces. I want to solve for the tension in each of the cables. And yes, they are listed up there for me. Those are based on a gravity value of 9.8. So at least we have a target to hit somewhere near there. If you feel like you really need to hit their numbers, use 9.8, whatever, who cares? If you're going to keep with 10 like we're doing with the class, just know your answer will be a little bit different, but that's completely okay. It's about the mechanism, it's about the process. So if I wanted to solve for one of these, let's see what we have. Okay. If we want to solve for any of these, we could clean these up a little bit. All right, let's use, if I called this equation 1 and equation 2, just so we can kind of keep things straight. If I take equation 1 and bring it down here, I would say T1, I can solve for the cosine of 60. So cosine 60 in my calculator gives me 0.5. So T1 times 0.5 is equal to T2 cosine of 35. So I'm going to type cosine 35 into my calculator. I get 0.82 times 0.82. I could solve for T1 so that I could then plug it into my second equation. I could completely do that. So if I did that, I would just divide by 0.5, divide by 0.5, cancels on the left. And I get T1 is equal to, let's see, I got 0.82 divided by 0.5, 1.64, okay, T2 times 1.64. All right, let's hold on to that for just a second. And I'm going to help you a bit with the second equation, but I want to leave some things for you to do. So we've solved for T1 to say, okay, that's T2 times 1.64. So if we go back to the second equation, mg, that's mass times gravity, okay? Mg, mass is 10, gravity is 10, so that'd be 100. If we like, just in case if you're coming back to this and you're not sure what I was talking about, this would be 10 times 10, mass times gravity, is equal to T1. We said T1 is T2 times 1.64. So we're going to replace T1, and we're going to say that is T2 times 1.64. I have to make some room. Let's see. Get rid of gravity for just a second. So, okay, mg right there. All right, so we've got times the sine of 60. So sine of 60, 0.87 plus T2 times the sine of 35. 0.57. All right, from this point, you can multiply, add, solve for T2. So you would end up with T2 equals blank. Then you could plug it into there and get T1 equals blank. I'm confident that you can do it, but if you need help, let me know. Let me know. I'm going to scroll up, get you started on number 2, then I'm going to give you the rest of class to work on this. Okay. Don't worry, all this stuff will show up in the recording. Okay, so for this one, they've given us the value of T1. They told us that it was 60 newtons. That was very kind of them. They want us to find mass, and they want us to find T2. So let's just draw out the things we know. We know 60 newtons has a component going to the left and a component going up. We know that T2 also has a component going to the right, along with a component going up. So the component going to the left of the 60 newtons, this would be 60 cosine of 55. The part going up would be 60 sine 55. For T2, we would have T2 cosine of 40. And going up, we would have T2 sine of 40. Going downwards, we have mass times gravity. If we looked at our summation of forces, this system isn't moving, so 60 cosine 55 is equal to Ti cosine of 40. Going down, we have mg is equal to going up 60 sine 55 plus T2 sine of 40. From that point, I'm confident you could solve that. I want you to, let me stop the share. Your assignment is to finish the sheet. I got number 1 really far along, so you've got a guide, some experience. For number 2, I just got it started, so you've got some ways to go. Number 3 is your challenge problem. You're going to run into